Welcome back, Mindsetters, to this Learn Extra session for grade 12 science. Guys, keep posting on the page. I'm loving what I'm seeing. I'm seeing you guys are definitely loving the show. So guys, I stress again, make sure you get on the page. By the way, John, we had a question from Tsepo. He says, Ty, I hear there are 7 electrolytic cells. Are we supposed to learn them all?
Okay, Ty, thanks. That's a really good question. Now, when we deal with electrochemistry, I haven't counted them all up. So electrolytic is about electrolysis. You certainly need to know about the production of chlorine. And there are 3 cells there. There's the membrane cell, there's the mercury cell, and there's the graphite cell. So you need to know those 3. You need to know the dangers and the environmental impacts of those. So that's one group of 3 that I'm aware of. You also need to know the electrolytic cell that's used for the recovery of aluminium. So that's another one. So I make it 4. I'm not sure about the 7. I suppose you could say that if you're looking at refining of metals like gold and copper, that's another type of one where they purify the gold and copper, where they do electroplating. That would be another one, but they're all quite similar, but they could change the metals. So don't learn them as particular ones. You could get in the exam where you've studied the gold cell, you might get one that's doing refining of nickel, but the principle is the same. I hope that helps it. I only count 6 though in total. So yeah.
All right. So then we also had another one from Nokulo. Sorry, I'm trying my best. She says, hi Ty, can you please ask John to explain how increasing concentration changes the rate of reaction time graph and the concentration time graph?
Okay, we will come back to that one in a little while. I just want to finish off this calculation. And then we'll get straight into that. Before we do some chemical equilibrium. Now, guys, I deliberately have left chemical equilibrium because I know that we want to spend a good time on that. But I don't want to just do KC calculations all the time. So tune in, make sure that you're with it, because this is a section that I know that a lot of you struggle with, but we want to make sure that from today on, you're going to ace KC questions. So let me answer this, then I'll answer that question, and we'll get on to KC in a minute. So here we go. Remember what we were saying? We had to do a calculation to verify that this was a spontaneous reaction. So what I've done is I went and looked on the values on the table, and I found that the iron-iron 2 reaction has a value of negative 0.44 volts. It's important that you write the negative in. Don't lose the negative. It's there. It's if you were using a half cell with iron and iron 2 plus, then connected to the hydrogen half cell, the standard hydrogen half cell, you would get a voltage reading on the voltmeter of minus 0.44. That would be because the iron is the anode. It is the source of electrons. It's where you're going to get oxidation. Anode, oxidation, the vowels go together. Okay, in this case, we find that for oxygen, the value is plus 0.4. That's telling us that compared to the hydrogen half cell, that this is going to be the cathode. So now when we connect these two together, we know that it is like a cell reaction. It's like the electrochemical cell. So we're taking something from electrochemistry to see if it's spontaneous. Remember, the galvanic cell is the spontaneous one. If you connect an iron 2 plus, an oxygen and water cell together, connect those two together, it will be a galvanic cell. You don't need to push energy in. And the calculation to confirm that is you do this calculation. Equation on the data sheet is given as, the formula on the data sheet is the E naught of the cell. The reading on the voltmeter is the E naught of the anode minus the E naught of the cathode. It also does it as E naught reducing agent minus E naught oxidizing agent. It also does it as E0 oxidizing minus E0 reducing. So we can make sure that we've got it right. I prefer the anode minus cathode, and I remember that's where oxidation, that's where reduction takes place. Now I sub in the values, and the first value, the anode value, was minus 0.44. You know what? It's the other way around. I've made a mistake. It's the cathode minus the anode. So I wrote down the formula wrong. Never do that. Remember it from the right check on the data sheet. It's cathode minus anode. And here we go. We're going to say cathode value 0.40 minus. Now this is where a lot of you sometimes make a mistake, because we've got to put a bracket around this value, and we're going to say minus 0.44. Now remember, when you've got a minus minus, it's always a thing to be careful about, because the minus times the minus gives you a plus, and the value that we're going to get is going to be 0.84. Now in this case it's volts, and notice it is a positive value. Very important that you recognize that this is positive. If it's a positive value, you've shown by calculation that it's spontaneous. If it turned out to be a negative value, then it would be non-spontaneous. Then it would be not a galvanic cell, but an electrolytic cell, the ones that we mentioned earlier. Okay, so right, let's go on to that question. Just repeat it again for us and for the viewers that might have missed it. The one about the reaction rates.
She wanted to find out how concentration affects the reaction rates and the reaction time graph.
Okay, so I'm going to just pick a set of axes here, and I'm just drawing them up quickly. So just give me a second, and we'll take a particular example. Do this one. We're going to say we have hydrochloric acid and zinc. Okay? And hydrochloric acid and zinc produces for us hydrogen and zinc chloride. Now, if we were to balance the reaction, we'd put a 2 in front of there, and now we've got a balanced reaction. Over here on the axes, I'm going to say that this is the volume of hydrogen produced, the volume of hydrogen in centimeters cubed, and this is time. Now, I haven't got the exact readings, but it's usually measured in minutes, can be seconds, but let's put it like that. So what do we know when we put some zinc and hydrochloric acid together? We get these bubbles of hydrogen gas, and we can measure the volume of hydrogen produced in a few minutes. So what does the graph look like? Well, in this case, the graph tends to be a kind of straight line, and then it starts to curve, and it does something like that. Now, they sometimes ask you about interpreting this graph, and they say, well, what does this tell you? At this point, we recognize that we've got more or less a straight line between those 2 points, between the top point over here and over here. That's more or less a straight line. The gradient is constant, and we've got a positive gradient, and we can say that the change in volume over the change in time is equal to the rate. Okay? The rate of reaction. Now, we'd have to say that there was a certain concentration of this one. Let's call this 1 molar. What is that's saying 1 mole per decimeter cubed, 1 molar hydrochloric acid. And that's the green line. What are we saying over here? We're saying that there's no more hydrogen produced. This says the reaction is at its end. It's ended. There's no new product. No new product. So it's over. Once it goes flat, it's finished. You with me? I hope so. Now, the question is, what would happen if we used a more concentrated acid? The same volume of the acid, but it was more concentrated. So instead of 1 mole per decimeter cubed, I'm going to use a different line now. Let's say I used a 2 mole per decimeter cubed sample of acid. So I'm going to use 2 mole per decimeter cubed. What this is saying, guys, is that this was time t. It took all of time t. Let's say that was 10 minutes to produce. I've doubled the concentration. I've increased the number of molecules that are present. They can move around. More effective collisions can take place. Okay? Got the same volume, but I've got twice as many moles of substance. Well, that tells me that they're going to react faster. And in this case, what we're going to see is that because we've got twice the concentration, remember, concentration is equal to number of moles divided by volume. And if we've got the same volume, the number of moles is equal to concentration times, that's right, the number of moles times volume. If we keep the volume the same and we double the concentration, we're doubling the number of moles. We're going to get more moles. So there are two aspects to this graph that are really important to take note of. We've got more stuff present, and we've got, so the chances of them colliding are going to be greater. So the end product, if we've got an excess, it's important, if we've got lots of this around, if that's in excess, then what we're going to find is our graph is going to look like this. It's going to be a steeper line, and it's going to be twice as high. So it's going to be up somewhere over there. I haven't even got space to do it. But the line will be twice as steep. So if the gradient of this was, say, 1, the gradient of this would be 2. It's increased in its speed. It's saying it's going to produce more stuff in half the time. So it would produce the same amount of stuff in half the time. That's generally, we don't ask specifics about it. You're just asked to draw sketches. So if we had half the concentration, well, the line here would be lower down. The gradient would be somewhere there. Okay. Often what they do is they say to you, you've got this, the one substance isn't in excess. So you've only got a certain number of reactions. The products then will be the same volume, and they can show you graphs like this. This would be less concentrated. This one is higher concentration. And concentration, I'm just writing as CO and C. Okay, I think we can just brief the chemical equilibrium question, and we'll make sure. Are there any other questions, follow-up questions to this one?
I think so. There was one from Bradley. He just wanted to find out, why is the reaction in galvanic cells always spontaneous?
Okay, remember, guys, galvanic cells. Those are the ones where you're using chemical energy to make electricity. So what do? We get a chemical reaction and we get energy out. That's the spontaneous. That's what galvanic cells do. Even your batteries at home, they are producing energy. They're producers of energy. So that's why they're spontaneous. An electrolytic cell is the opposite way around. We're going to need energy to make a chemical reaction. Okay? Now, under normal conditions, you're not going to find a less reactive substance reacting with a more reactive substance to give you a product. The more reactive substance always reacts with the less reactive substance. In electrolytic cells, you need to provide the energy to make the chemical reaction happen. Hope that answers it.
I think so.
Okay, let's just quickly flick to chemical equilibrium. I think it is on this page, and yeah, let's have a quick read through the chemical equilibrium question. So it says, the following equation represents a reversible reaction, and I just want to fill in some stuff here. The reversible reaction, double arrow, in a closed system at 470 degrees in a closed container. We're told that it's the ammonia production of ammonia. Nitrogen plus hydrogen gives us 2 lots of ammonia, and we're told that the delta H is less than 0. We're saying that's exothermic. Guys, give you a hint. Learn the Haber process reaction. This reaction often comes up in chemical equilibrium. So a change was then made, so it was at equilibrium, was made to the ammonia in the equilibrium mixture at T2. Okay? A graph showing the effect of this change is drawn below. The graph is not drawn to scale, but let's have a look at the graph. So we are dealing with a graph that deals with the amount of moles, and we are dealing with time. So there we go. And it's the gases versus time, the amount of gas versus time. So what can we read from this? I just want to get into it, have a look at it, and say to you, there's something's happened at T2. We know here we were in equilibrium, and here there's a change. So what's happening? Guys, you work it out. Tilt tie on the page. We'd like to highlight what you're saying. Have a careful look. The nitrogen is increasing. The ammonia goes straight up and then suddenly decreases. The hydrogen increases slowly. So which one, what factor is changing? Tilt tie on the page. We'd like to highlight the person that gives us the right answer, the first person, and we might even get in touch with you and send you a pack of winter school books. Let's go to a break, Ty.
All right. So mindset is, on that note, as John said, make sure you get on the page. Make sure you get chatting. So, guys, you can win a chance to get one of these sent to you. But for now, guys, we're going to see you after this break.